Geneticists make new discovery about how a baby's sex is determined. Medical researchers at Melbourne's Murdoch Children's Research Institute have made a new discovery about how a baby's sex is determined. It's not just about the XY chromosomes, but involves a regulator that increases or decreases the activity of genes which decide if we become male or female. The study, Human Sex Reversal is Caused by Duplication or Deletion of Core Enhancers Upstream of SOX9, has been published in the journal Nature Communications. MCRI researcher and Hudson Institute PhD student, Brittany Croft, is the first author. The sex of a baby is determined by its chromosome makeup at conception. An embryo with two X chromosomes will become a girl, while an embryo with an XY combination results in a boy, Ms. Croft said. The Y chromosome carries a critical gene, called SRY, which acts on another gene called SOX9 to start the development of testes in the embryo. High levels of the SOX9 gene are needed for normal testis development. However, if there is some disruption to SOX9 activity and only low levels are present, a testis will not develop, resulting in a baby with a disorder of sex development. Lead author of the study, Professor Andrew Sinclair, said that 90% of human DNA is made up of so-called junk DNA or dark matter, which contains no genes but does carry important regulators that increase or decrease gene activity. These regulatory segments of DNA are called enhancers, he said. If these enhancers that control testis genes are disrupted, it may lead to a baby being born with a disorder of sex development. Professor Sinclair, who is also a member of the Pediatrics Department of the University of Melbourne, said this study sought to understand how the SOX9 gene was regulated by enhancers and whether disruption of the enhancers would result in disorders of sex development. We discovered 3 enhancers that, together, ensure the SOX9 gene is turned on to a high level in an XY embryo, leading to normal testis and male development, he said. Importantly, we identified XX patients who would normally have ovaries and be female but carried extra copies of these enhancers, high levels of SOX9, and instead developed testes. In addition, we found XY patients who had lost these SOX9 enhancers, low levels of SOX9, and developed ovaries instead of testes. Ms. Croft said human sex reversal such as seen in these cases is caused by gain or loss of these vital enhancers that regulate the SOX9 gene. Consequently, these 3 enhancers are required for normal testes and male development. This study is significant because in the past researchers have only looked at genes to diagnose these patients, but we have shown you need to look outside the genes to the enhancers, Ms. Croft said. Professor Sinclair said that across the human genome there were about 1 million enhancers controlling about 22,000 genes. These enhancers lie on the DNA but outside genes, in regions previously referred to as junk DNA or dark matter, he said. The key to diagnosing many disorders may be found in these enhancers which hide in the poorly understood dark matter of our DNA. Funding acknowledgements. This work was supported by a National Health and Medical Research Council (NHMRC) program grant $1,074,258 to Andrew Sinclair, Peter Koopman, Vincent Harley, and an NHMRC project grant $1,031,214 to Andrew Sinclair. ARC grants DP 1501022120 and DP 1601044948 to Peter Koopman. Brittany Croft was supported by an Australian Government Research Training Program scholarship. Rajini Srinivasan was supported by NHMRC Early 608 Career Fellowship. Hubble uncovers black hole that shouldn't exist. As if black holes weren't mysterious enough, astronomers using NASA's Hubble Space Telescope have found an unexpected thin disk of material furiously whirling around a supermassive black hole at the heart of the magnificent spiral galaxy NGC 3147, located 130 million light-years away. The conundrum is that the disk shouldn't be there, based on current astronomical theories. However, the unexpected presence of a disk so close to a black hole offers a unique opportunity to test Albert Einstein's theories of relativity. General relativity describes gravity as the curvature of space, and special relativity describes the relationship between time and space. We've never seen the effects of both general and special relativity in visible light with this much clarity, said Marco Chiaberge of the European Space Agency, and the Space Telescope Science Institute and Johns Hopkins University, both in Baltimore, Maryland, a member of the team that conducted the Hubble study. This is an intriguing peek at a disk very close to a black hole, so close that the velocities and the intensity of the gravitational pull are affecting how the photons of light look, added the study's first author, Stefano Bianchi of Università degli Studi Roma Tre, in Rome, Italy. We cannot understand the data unless we include the theories of relativity. Black holes in certain types of galaxies like NGC 3147 are malnourished because there is not enough gravitationally captured material to feed them regularly. So, the thin haze of infalling material puffs up like a donut rather than flattening out in a pancake-shaped disk. Therefore, it is very puzzling why there is a thin disk encircling a starving black hole in NGC 3147 that mimics much more powerful disks found in extremely active galaxies with engorged, monster black holes. We thought this was the best candidate to confirm that below certain luminosities, the accretion disk doesn't exist anymore, explained Ari Laor of the Technion Israel Institute of Technology located in Haifa, Israel. What we saw was something completely unexpected. We found gas in motion producing features we can explain only as being produced by material rotating in a thin disk very close to the black hole. The astronomers initially selected this galaxy to validate accepted models about lower luminosity active galaxies, those with black holes that are on a meager diet of material. Models predict that an accretion disk forms when ample amounts of gas are trapped by a black hole's strong gravitational pull. This infalling matter emits lots of light, producing a brilliant beacon called a quasar, in the case of the most well-fed black holes. Once less material is pulled into the disk, it begins to break down, becomes fainter, and changes structure. The type of disk we see is a scaled-down quasar that we did not expect to exist, Bianchi said. It's the same type of disk we see in objects that are 1,000 or even 100,000 times more luminous. The predictions of current models for gas dynamics in very faint active galaxies clearly failed. The disk is so deeply embedded in the black hole's intense gravitational field that the light from the gas disk is modified, according to Einstein's theories of relativity, giving astronomers a unique look at the dynamic processes close to a black hole. Hubble clocked material whirling around the black hole as moving at more than 10% of the speed of light. At those extreme velocities, the gas appears to brighten as it travels toward Earth on one side, and dims as it speeds away from our planet on the other side, an effect called relativistic beaming. Hubble's observations also show that the gas is so entrenched in the gravitational well the light is struggling to climb out, and therefore appears stretched to redder wavelengths. The black hole's mass is around 250 million suns. The researchers used Hubble's Space Telescope Imaging Spectrograph (STIS) to observe matter swirling deep inside the disk. A spectrograph is a diagnostic tool that divides light from an object into its many individual wavelengths to determine its speed, temperature, and other characteristics at a very high precision. The astronomers needed STIS's sharp resolution to isolate the faint light from the black hole region and block out contaminating starlight. Without Hubble, we wouldn't have been able to see this because the black hole region has a low luminosity, Chiaberge said. The luminosities of the stars in the galaxy outshine anything in the nucleus. So if you observe it from the ground, you're dominated by the brightness of the stars, which drowns the feeble emission from the nucleus. The team hopes to use Hubble to hunt for other very compact disks around low-wattage black holes in similar active galaxies. The team's paper will appear online today in the monthly notices of the Royal Astronomical Society. The international team of astronomers in this study consists of Stefano Bianchi, Università degli Studi Roma Tre, Rome, Italy; Robert Antonucci, University of California, Santa Barbara, California; Alessandro Capetti, INAF, Osservatorio Astrofisico di Torino; Pino Torres, Italy; Marco Chiaberge, Space Telescope Science Institute and Johns Hopkins University, Baltimore, Maryland; Ari Laor, Israel Institute of Technology Technology, Haifa, Israel, Loredana Bassani, INAF Bologna, Italy, Francisco Carrera, CSIC Universidad de Cantabria, Santander, Spain, Fabio Lafranca, Andrea Marinucci, Giorgio Matt, and Riccardo Mide, Università degli Studi Roma Tre, Roma, Italy, and Francesca Panessa, INAF Istituto di Astrofisica e Planetologia Spaziale, Rome, Italy.